All right, folks, we're kicking off now. Good morning, good afternoon, good evening, wherever you may be. Welcome to the second of the Ringzer0 Return to workshops that we're offering throughout the holiday season. My name is Saumil Shah. I am the founder of Ringzer0 Training and also a Ringzer0 instructor. And I'll be presenting this workshop today, titled An Introduction to ARM64 Assembly and Shellcode. I'm going to share my screen with some instructions, and I'm going to leave it on there for a few seconds. Here are the instructions for today's workshop. The URL is called livenotes.exploitlab.net. Port number is 6502. In this URL, you'll find, once you open this URL, you'll find a notepad and a whiteboard. Click the notepad and keep it open. I will be using this notepad all throughout the workshop. Down below, you can find the link to the slides for the workshop. Please go ahead and grab the slides. It's a small PDF deck. Most of the stuff that we're going to do in this workshop is hands-on. And most importantly, once you've got the slides and once you're connected to the live notes, please follow these instructions on setting up the ARM64 Docker container. I'm mentioning this to you right away because it's about 250 megs of download, and in some cases, I've noticed that the downloads could be a little slow. So if you're intending to follow along and you've got a copy of Docker running, then you may want to start doing the git clone right away. The setup instructions are on the live notes. Please follow them. Once you finish the git clone, you would be building the ARM64 volume, which contains the file system for the ARM64 emulation that we're going to use. And then you may go ahead and build the Docker container. While you're doing that, while this is going on in the background, I'm going to kick off the main workshop and start with the content. If you've got any questions, feel free to pop them up in the Discord channel. Already. Yep. I'm going to keep an eye on the Discord channel from time to time. All right. I just need a little bit of screen real estate rearrangement time, as is the case with every workshop I teach. And there we are. Right. Okay, so formal introduction. My name is Saumil Shah. My Twitter ID and Mastodon ID are at the real Saumil and at infosec.exchange. I've been mucking around with cybersecurity for a very, very long time, since a couple of decades now. My recent experimentation has been with ARM binary exploitation. I started teaching 32-bit ARM exploitation a few years ago, then started working on IoT devices. Along the way, I wrote the Emacs framework, which is now what I use to actively emulate IoT devices in my class, and a number of people use Emacs for research purposes. Quite a few students of mine have found 0 days in IoT devices using emulated instances under Emacs, which makes me really glad that the tool's working as advertised. This year is a bit special. Midway this year, I decided I want to teach something new for 2 primary reasons. I also want to learn something new. and I want to get good at it. So I started building up the exploit lab for ARM64. What you're seeing today in the workshop is my very first public presentation on 64-bit ARM exploitation. Now, this is going to be a two-hour workshop. We're going to scratch the surface. What I wanted to present is an overview of what the ARM64 landscape is and what it's going to take, what are some of the nuances, and what it takes to get started with ARM64 and ARM64 exploitation. So the agenda is we're going to do a quick introduction to ARM64. I'm going to point out some very quick key differences between the ARM32 world and the ARM64 world and what has changed along the way. And then we'll dive into some hands-on stuff with ARM64 assembly and end the workshop with writing a simple shellcode. This is going to be the tip of the iceberg. There is a lot of stuff in the ARM64 world, which we simply do not have time to cover in the workshop. Right. So first, I'm going to give you a very quick tour of the ARM64 Docker container that you're downloading right now. When you run the Docker container, it'll give you a Docker environment. And inside the Docker container, you have a QEMU for ARM64, which will run a Linux, 64-bit Linux on an emulated ARM CPU. All the stuff that we're going to be doing will be within this ARM64 system. Instructions on how to start the Docker container are enumerated from slide number 11. In the rest of the Docker environment, you have a utility called ARM64 Docker Shell, which is basically like opening up a new terminal into the ARM64 environment. Now, in the Docker world, things are a little different. If you have a virtual machine, then what you do is you just start the VM. That's where you get the console. And then you open up multiple terminals because you want to type in your commands and you run a debugger in a terminal and something like that. In Docker, we don't have the concept of new terminals. So there's a little utility I've created called ARM64 Docker Shell, which you can open up a terminal window in your host and then use ARM64 Docker Shell to attach to the Docker environment as if you're just using it like a virtual machine. And then there's a shared directory, which we don't really need to get into. A bit about what we're going to see, what the environment is like. The ARM64 environment is a standard Debian on ARM64, running on a Cortex A72 CPU, which is an ARM v8 architecture, a fully 64-bit system. If you have a Raspberry Pi 4, you could do the same thing on actual hardware as well, provided you have a 64-bit Raspbian running on it. For all practical purposes, what we're going to do on the emulator is the same as what you do on the on a real-life Raspberry Pi 4. We're going to use the GNU assembler today, a little bit of assembly code I'm going to write, and we're going to use the GNU debugger. GDB is like the main workhorse for all our testing and R&D when it comes to ARM assembly. I'll explain a little bit about GDB in a moment. First thing I want to now give you is a very quick introduction to the world of ARM64. First of all, there's some confusion in nomenclature. On the Linux side, especially the GNU side, you will see terms like ARM64 being mentioned. In the Microsoft world, you'll see ARM64 being mentioned. Even in the Mac OS world, it's all ARM64. Well, both of them are kind of the same thing. The GNU toolchains used to be called ARM64 and the nomenclature stuck. And the Apple and the Windows environments call it ARM64. But for all practical purposes, ARM64 and ARM64 is the same thing. we will be using the more intuitive term ARM64 to refer to 64-bit ARM CPU and 64-bit ARM 64-bit Linux operating system running on it. Okay. ARM is a RISC CPU. So it is, RISC stands for Reduced Instruction Set Computer, which means that it is built for performance by simplicity. The simplicity lies in a limited set of instructions, as opposed to something like Intel, where you have a vast number of instructions being offered. When you have few instructions, the processing becomes simple. The burden of complexity is left to the software and the compiler, and optimizations in the compiler space. Second, just like its predecessor ARM32, ARM64 is also a fixed width instruction set. All instructions are fixed. Strangely enough, the size of the instruction is not 8 bytes per instruction. It is still 4 bytes per instruction. The registers are all 8 bytes wide or 64 bits wide, but the instructions are still 4 bytes wide. It may initially seem a bit surprising, but the reality is 4 bytes instruction size for the ARM64 CPUs makes sense, because not only can the ARM64 CPUs run 64-bit environments, they can also run 32-bit processes in a 32-bit subsystem. And therein, where you have a 32-bit subsystem running, it makes sense to have the instruction size as 32 bits, because the fetch, decode, execute circuits can be optimized just for 4 bytes. And 32 bits is enough space for representing a number of instructions. For us, when it comes to shell coding, this is going to be a bit of a challenge, but we will see this in a little while. I'm going to give you a preview of what registers we're going to use in just a little bit. But two things. All registers are 64 bits wide, which means all data that can be stored in the registers is 64 bits wide. Integers will be 64 bits wide. Now, when it comes to integer, I don't mean the C representation of integer, but the contents of a register will be 64 bits wide. And pointers will also be 64 bits wide. Now, there's a little bit of discussion we need to have about the relevant bits of a pointer, but for all practical purposes, the pointers are 64 bits wide. When it comes to the memory space, a 64-bit CPU does not mean that you have like all the 2 raised to the power of 64 possible addresses in the memory space. Neither does the x64 space have it, nor does the ARM64 space have it. Your virtual memory for most general purposes will be 48 bits on an ARM64 CPU. The top bits are just not used. The way the virtual memory is divided is also slightly different. You basically have the top half of the 48-bit space dedicated to user space, and the bottom half is dedicated to kernel space. And there's like an unused, unaddressable gap in between. This workshop is not going to go into details of the 48-bit mappings to 64-bit virtual memory, but this is just something I wanted to say. Now, in some ARM CPUs and some modern kernels also support 56-bit addressing with different page table mappings and so on. But that's another separate topic as well. When it comes to privilege levels, the ARM64 CPU has 4 exception levels: EL0, EL1, EL2, and EL3. The ARM32-bit CPU had 7 or 8 exception levels, which was vastly different. And this year, they've simplified the exception levels now. As far as registers are concerned, the ARM64 CPU has basically 32 registers and a program counter and the flags register, which is called P state, process state. We'll see a little bit of detail about these registers in the next few slides. And lastly, there are very strict alignment rules that have to be followed when it comes to memory access. Everything has to be 8-byte aligned, except for the stack pointer, which has to be 16-byte aligned. Now, in ARM documentation, in the 64-bit documentation, you will come across terms like word and double word. Now, in the 32-bit space, right, a word is the size of integer, which is 4 bytes. In the 64-bit space, a word is still 4 bytes. And a D word, a double word, is 8 bytes, which is the default register width. The definitions of integer, long, and all of these will change in a slightly not intuitive way when it comes to the 64-bit space. We will explore all of these with a program. Right. I think there's a question on here. Never mind. Okay, let's talk about the registers. Now, there are a number of registers. The representation may seem confusing at first, so I'm going to demystify this. The registers are given labels X0 through X31. Interestingly enough, you can also refer them as R0 through R31, just like what you did on the 32-bit ARM CPUs. But in this case, it is preferred to use X0 because we do not want to confuse ourselves with whether it's 32 bits, whether it's 64 bits. Both X0 through X31 and R0 through R31 refer to 64 bits width. The next question you might have in your mind is, okay, so what the hell are these W0 through W31 doing? I'll get to those in just a minute. First, let me explain the purpose of these registers. Being a RISC CPU, just like every other RISC CPU, you have lots and lots of registers. The philosophy of every RISC CPU is basically keep information in registers as far as possible. Very rarely do RISC CPUs like to use the memory. Memory access is expensive and it is avoided if possible. Now, what do you want to use registers for? You'll use the registers to do your computation. And if you look at the most fundamental building block of a program, it is the function. In most simplest terms, a program is nothing but a collection of functions or subroutines which get called here and there. So registers are also used for handling functions. And when it comes to functions, we have to pass parameters to functions. The first 8 registers, X0 through X7, are used for passing parameters to functions. And these are treated as volatile registers. That means they can be overwritten. They do not need to be preserved across function calls. The ARM32 CPU had, you could use 5 registers, you could use 4 registers to pass parameters, X0, X1, X2, and X3. In the ARM64 CPUs, you can use 8 registers to pass parameters. X8 is not used for parameters, but in several cases, X8 is used for the syscall number whenever we're invoking a system call. Registers X9 through X15 are called scratch registers. They can be used to hold any data, scratch data, which means results of computations, values to be calculated, and so on. The word scratch implies that these can be scratched off. These do not need to be preserved across function calls. Then there's a slight nomenclature confusion. Registers X16 through X30 are called scratch registers, but they need to be preserved across function calls. Now, X29 and X30 are somewhat special registers. They can be used as general purpose registers, but their purpose is a little special. X29 is also used as the frame pointer, and X30 is used as a link register. Now, for those of you familiar with the way link registers work in ARM32, it is the same. The link register is used to store return addresses from a subroutine. In ARM32, you could call it LR, and an assembler would understand it. But here, they have not chosen to give names like LR. Instead, this register is always referred to as X30. You saw a little question popping up on Discord. Yes, this workshop is being recorded, and the recordings will be made available sometime just a little after New Year's. And you keep an eye on our announcements on our social media accounts, and you'll see when we publish the workshops. All right, coming to the two important registers, X31. Now, this register is a dual purpose register. Initially, it's a little difficult to understand. But X31's main purpose is that it is the stack pointer. The stack pointer will point to the top of the stack. But the stack pointer is applicable only when used in instructions that manipulate the stack. That is, it will only work as a stack pointer in load store instructions. If this register is used in any other instruction, it will function as a 0 register. It's also called XZR. A 0 register does nothing except return 0. Whenever you read it, it will be 0. Like, okay, what's your value? 0. If you're referring to X31 during push and pop or stack operations, it will show the stack value. If you refer it other than stack operations, it will show you a 0 value. I'm simplifying this a little bit, but that's basically, this register behaves differently when it comes to different instructions. Now I want to talk about what are these W0 through W31s. The X registers are D words, double words, 64 bits. The W registers are subsets of these main registers. That is like a word subset. So if you look at X0, it'll give you a full 64-bit value. W0 will only give you the lowest 32 bits in that, the lowest 32 bits in that register. Same with all the other ones, W1 all the way through W31. Then we come to the program counter. The program counter is always going to be 64 bits. Last, you have the P state register, which is the flags register, which basically contains status like negative, 0, carry, overflow, and what your current exception level, the privilege level is. Right. There's a question about, is it like ARM32 PC always points 2 instructions ahead? We can take this question slightly offline. Let me see if I have any time after the workshop. I will come back to this one. The short answer is it is not so simple. Okay, now let me get to stark differences between ARM32 and ARM64. So here we go. First of all, there's no more thumb mode. You don't have any smaller widths instruction. If you're in ARM64, that's it. 4 bytes instructions, 8 bytes registers. There's no stepping down. Now in ARM32, you could step between thumb mode and ARM mode at will at any time in the process. In 64-bit space, you can't switch to 32 bits and 64 bits as you like it. It does not work that way. Your process can either run entirely in 32-bit space, or it can run entirely in 64-bit space. There's no interworking, there's no switching back and forth. Next big difference. In ARM32, some instructions were allowing to specify multiple registers. Like you could push multiple registers at a time, push R0, R1, R2, R3. You could push like all 10, 20, 10, 15 registers all together at a time. You can pop them too. You had instructions like load multiple and store multiple as well. Now, ARM64 has completely done away with this concept of register sets. At the most, you can specify 2 registers per instruction, no more than that. So, what happens to if you want to push multiple registers on the stack? Well, do it the good old Intel way, one at a time, with one exception. I'm going to cover that exception when we do some hands-on stuff with the stack. But for now, you cannot push multiple registers. You cannot pop multiple registers. Basically, there's no instructions which will let you operate on multiple registers at a time. The whole concept of the register set is gone. The other big difference is in ARM32, you could use the program counter, stack pointer, link register in any instruction. There was no restriction. You can do multiplication of the program counter. It'll screw up everything, but you can still do it. Nobody stopped you from doing that. Now, the use of program counter, stack pointer is restricted to only a few instructions. You can't use these registers in any instructions of your choice. What that means for shellcode, it's getting tougher. What that means for ROP gadgets, it's getting tougher. Next up, you don't have conditional instructions anymore. In ARM32, you would have something like add GT, add greater than, or add LE, add if less than equals. Nothing of that sort now. Every instruction is going to execute. The conditional part is only limited to conditional branching, which of course was there. You could do like branch if equals, branch if not equals, branch if greater, branch if less than. So conditional execution is only restricted to branches. All other instructions do not have conditional bits at all. Performance studies have shown that with modern pipeline CPUs, which basically have branch prediction and instructions caching and all that, conditional execution doesn't give you any extra advantage as it did before instruction caches and branch predictions came into the hardware stage. So the good folks at ARM did away with that, saving a few bits for use in the general purpose instructions. And lastly, even though you have stack operations, there are no dedicated push or pop instructions. You have to use load and store instructions for these. So that's like a short summary between these two architectures. There's a lot more that we could talk about, but for this workshop, we're limiting our discussion only to just a little bit of assembly necessary to write some simple shellcode. For those folks who have been joining in a little late, I've seen questions being asked, especially about availability of this workshop. Please set your minds and hearts at ease. The recordings will be available, not immediately, but keep an eye on our social media accounts when the recordings will get posted out. Also, for those who are attending, you will see a little present in your inboxes tomorrow. For those who are not attending, no presents. Sorry. Okay. We're going to use GDB now for, we're going to very quickly get into the hands-on stage. All the GDB stuff that I'm going to be using is enabled with GEF, which is the GDB enhanced features. GEF makes GDB usable and bearable. And once again, we have GDB available for 64-bit ARM debugging. And this slide is basically just a cheat sheet about a few GDB and GEF commands. Let me skip that. Okay. Quick round for any questions that you may have. And then I'm going to get into the setup of the Docker container. I'm going to keep an eye on Discord. If there's any few questions, pop them up now. All right. Quick, if I'm going to post a little poll on Discord. I want to see who's following along on Docker and who's not. I'll just set up a quick poll. Give me a second. Moment. Okay, so we've got a few folks, about 6 folks, following along with Docker. Okay, 7, 8. Well, no problem. If you're even not following along on Docker, you can take this recording and follow it along, especially when you're extremely bored over the Christmas holidays and have nothing better to do. Okay, time to set this thing up. So once you've done all the git clone stuff, the first thing you want to do is open a shell and run ARM64 Docker. When you run this for the first time, it's going to take some time because it's going to unpack the entire file system. You see a little progress bar. So yeah, thanks Nation for pointing it out. Yes, the first time you do this, it's going to take some time. And then very soon you will be dropped into an ARM64 Docker prompt. I typically leave this part. I don't use this as a main workspace. The only thing I'm going to do in that workspace is run this command called ARM64 start. This will fire up QEMU and the emulated environment. And after a minute or two, you should see this console only prompt come up, which means that the ARM64 environment is ready to use. I'm going to perform these steps side by side as well. But first, I want you to walk through this. Okay, I see a few errors. All right. Okay. I see there are some errors coming up. And I'm just hoping that the kernel is not messed up. I'm going to take a short break for about 5 minutes. Don't worry. I will get this thing fixed. And it's good time for a short pause. We'll be back in about 5 minutes. Please don't go away. Okay, folks, the issue is fixed. It was a git ignore issue, and GZ files were somehow just getting ignored. I believe I fixed it. I've pushed it to the repository. What I'd recommend you do is go to the ARM64 Docker and just perform a git pull, and then try to basically exit the Docker container, start this whole thing again, and react to this message with a thumbs up if it is working. If you folks have successfully been able to perform a git pull and grab, and you see the image 5.10.7.arm64.gz appear, please react with a thumbs up to my message in Discord so I know everything's going swimmingly and that there's no more git issues that I have yet to fix. Okay, I'm going to once again go through slides. I'm going to now follow on. I'm going to now follow along and perform these commands myself and sync up to the state. So once again, we did the git stuff. We did the build, ARM64 Docker, ARM64 volume. Now we're running the ARM64 Docker. Inside ARM64 Docker, we're now executing ARM64 start, and that should hopefully go through. I'm seeing a few of you have reacted positively, so that means it's the git fix is working. And then it's going to land you to the console banner. I'll give you what's coming up next, and then I'm going to proceed and do all these things. When we end up at the console banner, you want to then open up a new terminal window on your host and just attach to ARM64 Docker shell using this command /ARM64 Docker shell. And that should bring you up this green menu, which will give you three choices. Either you want to land in the Docker shell, or you want to land inside the emulator. And please choose to land inside the emulator's user shell. Okay. All right, I'm seeing a message. Yes, I'm going to edit the instructions. We will need to build the Docker container once again. We will need to build the Docker container once again. Thank you very much for that note. And I will add this instruction into the live notes as well. All right. Thank you for the info, folks. I'm going to do this on my own system and show you how it goes. Okay, so my first one, I'm going to do the run ARM64 Docker. I usually like to have 3 panels. I'm at this ARM64 Docker prompt, and I'll perform an ARM64 start. It takes a little bit to boot. That's okay. Okay, I've got my console-only prompt here. So now I'm going to start with the ARM64 Docker shell. Now, if you somehow you don't get this ARM64 Docker shell menu, sometimes it may happen, like if the system hasn't booted up fully, you might end up landing into just something like this, which says ARM64 Docker in blue. And you want to get the menu back, the command is /shell menu, and that'll bring you the menu back. So in case you get stranded in the ARM64 Docker shell and you don't have this beautiful teal colored menu, just do a /shell menu and everything's going to come back. I'm going to launch 2 of these. And in both of them, I'm going to drop myself to the ARM64 emulator user shell. And you get this green prompt. It says ARM64. This is the 64-bit Linux environment on ARM. If you just type in ls-cpu, you will see that you're now running on a Cortex A72 CPU. And the CPU is 64-bit architecture. The operation modes supported are in 64-bit mode and 32-bit mode. And then there's a number of other little details about the CPU, which we're not concerned with at the moment. Okay. Once you have this, I want you to go ahead and grab all the interesting stuff that we'll use to play along with. So within the ARM64 shell, perform a git clone. And this repository called Return to Workshops contains all the little snippets that we're going to use today. I'm going to put these instructions on the live notes as well. Okay, the instructions are on the live notes. I'll also drop them in Docker. There you go, git clone this stuff. Okay, git clone. Okay, here it is. You should see a directory called Return to Workshops. And in this directory, you have a number of interesting stuff that we're now going to play with. So let's get into the directory and start. The first demo I want to give you is a little bit about the 64-bit address space. Moment. Let me show you this file called var64.c. What I'm going to do in this is show you what the fundamental data types look like. I also want to give you a very quick introduction to the 64-bit user space. We'll play around a little bit with GDB and get a feel for what the memory layout is like, what the addresses look like, and things like this. So this is a simple program. I have 4 variables inside a function called function1. You have integer a equals 5, long b equals 6, character pointer c, and integer d equals 7. If this is 32-bit space, right? So for 32-bit space, I'm going to write what the sizes are. The size of this is 4 bytes. Int and long are going to be the same. So size of this guy is also going to be 4 bytes, long b. Pointers, again 32 bits wide. Size of this character pointer is also going to be 4 bytes. And size of this integer is going to be 4 bytes. Everything's going to be 4 bytes. I will show you this. There's actually a binary I have specially compiled on my own system called vars32. You folks don't have it? But I want to show you this binary simply to illustrate the size of these data types. So if you run this is still running on a 64-bit memory space, but it's a 32-bit process. If you run this, you notice that the sizes of A, B, C, and D are all 4 bytes, which is as expected. And the addresses are also 4 bytes long, even though it's being displayed as 8 bytes long. Now, in the 64-bit space, what's going to happen? Now we're going to do this together. Just go make vars64.elf. And we're going to run this. And we're going to see what the results look like. Once you've made it, run it. Now notice what the changes are. In 64-bit space, integer is 4 bytes, but long is a double word and it is 8 bytes. Pointers are also 8 bytes long. So this is the change that has occurred. As to the locations of these variables, local variables live on the stack. A is a local variable, B, pointer to C is a local variable, and D as well. All of these have stack-bound addresses. And you can see the stack addresses are like 0000, FFFFFF, EE1C. All of these are in the FFFF range, addresses of A, B, C, and D. Now the contents of A is 5, B is 6, D is 7. You can see that in the output over here, A is 5, B is 6, and D is 7. What about the contents of C? Now, C is a pointer, and C points to the heap memory. malloc will return you 40 bytes from the heap. And heap addresses are at 0000 AA something in the memory layout. We're going to run this now in a debugger, and we're going to see what the 64-bit memory space looks like inside a debugger. To run this in the debugger, we simply use GDB /vars64.l. It's taking some time. It's a little slow. Here we go. Now, I'm going to list the program. I've compiled it with debugging support. And I want to set a breakpoint at line number 30. So I want to be able to inspect these values before they get printed. I want to set a breakpoint at 30, and then I'm going to run the program. If you're interested more in how to debug using GEF, ARM programs using GEF, please refer to my workshop that I did at Catch 2022. Sorry, not Catch 2022, at Back to Vegas 2022, which was delivered on the 7th of July. The video is available on the Ringzer0 Workshop's website as well. And that is a more comprehensive workshop on how to use debugging features. For now, I'm going to assume that most of us are familiar with the basics of GDB. We'll set a breakpoint at line 30, and then I'm going to run the code. When you run, you first see all the registers. And GEF does a nice job of highlighting which register points to the code, which points to the heap, which points to the stack, and which registers may be a string. So here you can see X0 points to the heap, X19 and X21 point to code. These other ones are different values, point to some various parts. And X29 is a link register, which points to the stack. Sorry, X29 is a frame pointer, which points to the stack. X30 is the link register, which points somewhere in the code. Stack pointer is, of course, points to the stack, and here's your program counter. So that is the registers, then you have the stack, and now you have like these lines of code that will execute. I want to show you what the process virtual memory map looks like in 64-bit space. In 64-bit space, this is your process virtual memory map. I'll paste this in live notes as well. So here you can see the binary is being loaded at AAAAA000. This is the lower addresses. It doesn't begin at all zeros. It begins at AAAAA, goes down. The libraries are loaded at FFFF7. And you can see the stack is at FFFFD. This is the stack. This is the binary var64.elf. This is libc. This is the loader library. And here is the stack. The upper 2 bytes will always be 0000, no matter what. Only these 48 bits are being used. These 16 bits are not used at all. Not in the user land, that is. They're only used in kernel space. Now, kernel memory will be all FFFFF. These will be all FFFF. Unfortunately, we can't see the kernel memory from user space debugging. So the user land all memory addresses will be beginning with 2 null bytes, always. If I am to show you where the variables are, if I say print address of A, so A points to FFFFFE0C. We have to manually look up where it is in this process memory layout, or we can use one of GEF's nice features and just say xinfo &A. And xinfo will tell you that, oh, this is this variable A, this address of A, it lives inside the stack. Makes it easy for us to identify what's over where. Similarly, you can inspect xinfo &B, &C, C also. All of these live in the stack. But if you perform an xinfo on the contents of C, you'll see that C is a pointer. It's a character pointer. It is also 64 bits wide. And this pointer points to the heap. The address of the pointer is AAAAB22A0. And it says the path name is heap. If we look at the virtual memory map, this green colored part is the heap. It is living between the binary and the shared libraries. So this was a little bit about the 64-bit address space. Now we're going to go on to a little bit of assembly. And we're going to start with first.s. The first.s is a collection of some simple assembly instructions. And here we can see some nice syntax variations as well. The first instruction is a move. In move immediate, so the first instruction will basically set x0 to the value hex 1234 on line number 5. Line 6 and 7, move x1, x0, move x2, sp. These will basically just take the value of the destination, the destination register and set it into the target register. So x0 will be copied into x1, stack pointer value will be copied into x2. The next 4 moves are very interesting. You have a move Z. And this is applied to register x4. The value that is being moved is 4142. And what you see suffixed over here is a shift left. What will this do? So move Z will copy everything, copy this value and prefix everything with zeros. So the first leading bits will be zeroed out. This value 4142 will be copied into the register at the lowest bits. And then all of these bits will be shifted left by 48 positions. Next, you have move K. Now, this is really interesting. The K stands for keep. It will keep all the bits in X4 as they are and set new bits into it. And these new bits will be 43, 44 shifted by 32. The third instruction down here is also move K, which will set these bits 4, 5, 4, 6 and shift them 6 by 16. And the last one is 47, 48, no shifting happens. At the end of this, what do you think the value in X4 is going to be? Let's find out. Okay, here's a question. What's the default behavior of move? Does it act like a move Z or move K? So truth is, move is not really a full instruction in the ARM64-bit set. It is a pseudo instruction. It will get translated to either move Z, which is the default, or an OR instruction. Because in this move instruction, not only can you move just immediate values, you can also move bit patterns, and that translates into an OR instruction. If you actually read the ARM64 instruction manual documentation, it is dense, and there's a lot of little nuances that are documented. It takes a while to digest it. But yeah, short answer is it acts like a move Z. Now let's assemble this. I've got a little script to do that called build ASM first.s. It'll assemble it. Let me show you a quick disassembly too, using object dump. Now here's first.o. If you look at the disassembly, you can see all these instructions are 4 bytes long. So here's your first move, then the move x1, x0, move x2, xsp. This instruction is already showing you the shifted. I mean, it's applied the shift here. It's become a move x4 with 4142 0 0 0 0. These are the move Ks. And the last one that you see is a BRK0, that's a breakpoint. So we're going to run this under GDB. It's assembled it to an ELF binary. We'll run this all the way to the breakpoint. So when it hits the breakpoint, you're going to get control in the debugger, and we'll see what values result over here. If I do a disassemble underscore start, you'll see the same disassembly here. And I'm going to run. When you run, let's go scroll up and see the registers. So x0 became 1, 2, 3, 4. Then x1 became x0. x2 is loaded with the value of the stack pointer. x3 is nothing. x4, the value of x4 is 4142, left shifted by 48 bits. Then with a move k, 43, 44, left shifted by 32, 45, 46, left shifted by 16, and then 47, 48. This is how you got like an arbitrary 64-bit value into a register. You can achieve this by a maximum of 4 move Z and move K instructions. Next, I want to show you a little bit of PC relative addressing. And that's a file called pcrelative.s. Here again, notice the syntax is slightly different. This instruction is an LDR instruction. It behaves, it's more or less the same as the LDR instruction in ARM32. But you notice that LDR stands for load register from memory. So X0 is the register that's going to be loaded. And this 64-bit D word, FEDCBA 98765432110, will be placed in a literal pool at the bottom of this code. And a PC relative reference will be generated for this literal pool address. And the contents will be then placed into X0. The next is an add instruction, which is also PC relative. It's ADR. Now, in the ARM64 instruction set, ADR is an official instruction. In ARM32, ADR was a pseudo instruction, which translated into add register, PC, offset. Here, ADR will imply it's a PC relative instruction. So LDR and ADR are both PC relative. This string is a label, which is over here, and it is going to be resolved in PC relative terms. We're going to then do a build ASM. We built it. I see a question popping up. Oh, definitely. We'll give some references towards the end. Can you definitely remind me at the end about some references? Deeply appreciate that. I'm going to continue with the PC relative stuff right now. Let's run it. If you look at the disassembly of these LDR instructions and the ADR instructions, you will notice no reference to the program counter in there at all. If you do a disassemble start, all you see is LDR, the register, and the offset. It is implied that this offset will always be given to the program counter. Now, what's going to be at these offsets? Let us see. I'm going to examine the memory. X Let's run this. Hits the breakpoint. And you can now see that X0 contains this value FEDCBA, and X1 contains this, is a pointer to the string hello world. If I show you the disassembly using object dump, let me do that over here. If you look at pcrelative.o, if you see this disassembly, here it says LDR X0, 20. So this is the value of program counter plus 20 bytes. And that ends up being over here. And this is the 64-bit value that's getting copied into X0. ADR is basically going to add X1 with the address of PC plus offset. And that's going to be the string hello world. And that string is over here. So this is how PC relative addressing and literal pools work on ARM64. A lot more can be discussed about it, but for now, I just want to show you some more stuff and very quickly move on to shellcode. The next thing I want to show you is about stacks and how stacks are used, how stack is used. How do you push and pop values on the stack? And here you have stack1.s, stack2.s, and then we have stackpair.s. We're going to build all of these. The stack1.s gives you an idea of how to push and pop stuff on a stack. Now, in ARM32, we had the ability to push arbitrary number of registers. You could push all the way from R0 through R15, all onto the stack. Here, you cannot do that. You can push. Now we're not going to call it push, we're going to call it store. We can store one register on the stack at a time. The notation is quite similar to the ARM32 style. So this notation basically means pre-increment or decrement, pre-indexed, and this notation with LDR is post-index. I'll demystify this in just a little bit. This is a move X1 with some arbitrary value. And then what we're going to do is we're going to copy this X1 onto the stack. The next instruction, store X1 at stack pointer -8. This is what it means. So what this means is, first you do stack pointer equals stack pointer minus 8. And then at the resultant address, you store the content x1. This is what this instruction does, the store instruction. It's a push. So you lift the stack pointer up, place the value immediately there. The stack pointer still points to the top of the stack. Next, what I'm doing is I'm zeroing it out. I'm doing move x1 xzr. I told you xzr is a 0 register. So this instruction at line 15, this will set x1 equals 0. So the store is like a push. This LDR is going to be a pop. The way pop is going to work is x1 will be loaded from this stack pointer, and then stack pointer equals stack pointer plus 8. This is post-indexed, where the 8 is left outside the brackets. In pre-indexed, you have 8 inside the brackets and a bang at the end. Post-indexed, you have the 8, the index outside the brackets. This notation is the same as ARM32 assembly. Let's save this and let's see this in action. So here's the code, disassemble start. And I'm going to set a breakpoint at the first instruction and then single step through to show you how the stack builds up. I'm going to run it. So waiting at the breakpoint, the first instruction is going to be executed is the move with x1. This panel over here shows you the current stack. So right now, there's something on the stack, and this is the stack pointer pointing. The address of the stack pointer is EF70. I'm going to single step through the first and the second instructions. 2 instructions I'm going to single step through. So now the move has executed and the strx1 has executed. So you can see the move has set x1 to 1337, and the str instruction has reduced the stack pointer by 8 bytes. So stack pointer got subtracted by 8 bytes, and this value get copied at the stack pointer. So this is your push. Now I'm going to move x1 xzr. It will be 0. So now you see that the stack pointer has become, the x1 has become 0. And the next instruction, LDR, is this LDR instruction is going to load x1 from the stack pointer and post increment the stack pointer by 8 bytes. I'm going to step through this now. Now you can see that x1 is back to 1337. The value got popped off the stack, and the stack has now come down to EF70. So this is how push and pop works. Here's an interesting question. Do you need to be 8 bytes aligned to push in the stack? The answer is yes and no. Yes, you have to be 8 bytes aligned, but you actually have to be 16 bytes aligned to push into the stack. Stack pointer alignment is preferred to be 16 bytes aligned. So 2D words aligned together. That is what the ARM architecture procedural call standard states. Now, in some kernels, there is privileged code which can enforce this behavior in hardware. You can turn this behavior on or you can turn this behavior off. I have seen on my Raspberry Pi, it is turned on. So if you try to perform a second push on top of this, it will cause a problem. But in QEMU, somehow it is not enforced. The second push will still go through. But now this means that, okay, if you want to push multiple registers, does that mean that you have to like waste space? Like after every 8 bytes, you have to have another 8 bytes gap because the stack pointer must be 16 byte aligned? No, not really. Turns out that the designers of the ARM instruction set have studied compiled code very, very thoroughly. And if I show you this code, stack pair.s, you now have some different instructions here. In stack pair, pay attention to lines 15 and 18. Line 15, you have STP, which means store pair of registers. So store X1 and X2. At SP minus 16 bytes. So really interesting things happen over here. First, the stack pointer is going to be decremented by 16 bytes. Then X1 and X2 are going to be written. X1 will be at the top of the stack and X2 will be at SP plus 8 after it has been reduced by 16 bytes. So it's like you push, it appears to have been pushed in reverse order. So basically it happens in one go. You lift it up by 16 and then write X1 and X2 in succession. Then here I'm going to zero them out to prove that they have been changed. And this LDP is like a pop instruction. So this is going to be something like push X2, push X1. And this is going to be like pop X1, pop X2. Let's run this. I'm going to again set the same breakpoint at the start and step through this and show you. So I'm going to run. I'm going to step through two instructions. So the X1 and X2 are going to be set to 1337, 1338. They've indeed been set. And now we're going to use this STP instruction. X1 and X2 are going to be posted at, they're going to be like posted at the stack pointer. First, the stack pointer is going to be lifted up. Its currently value is EF60. It's going to become EF50, and then X1 and X2 are going to be copied over there. Step through one instruction. Now you can see that X1 is over here at the top of the stack, immediately followed by X2. Again, let me step through the two X1s, like move zeros. They're zeroed out. The next one is a pop instruction. So X1 is going to be copied from the stack pointer. X2 is going to be copied from the stack pointer plus 8. And then the stack pointer is going to be incremented by 16 bytes. That's what's going to happen in the LDP. So after the LDP, there you go. These values are back in X1 and X2 again. And the stack is back to where it started. So this is how the stack works. Next, what I want to show you is how syscalls work. And where we're leading with this is we're actually getting closer to writing some simple shellcode, an exec-v shellcode which will drop you into a shell. Now to write shellcode, we need to write a number of syscalls. I want to show you very quickly how syscalls work, again through an example. And here we're going to use testsystem.c as an example of syscalls. We're going to compile this. So here's testsystem.c. It's basically just a wrapper around the library call called system. What we want to do is we want to run this C code, and then we want to find out the underlying system call and mimic it in assembly. I'm placing all these instructions in live notes as well. If you run testsystem.elf, it drops you into a shell. You can exit the shell, you come back. But now I'm going to strace it. And here's the strace command. What strace does is it shows you all the syscalls that are invoked. And we particularly want to focus only on the exec-v syscall, nothing else. So I run this. The first exec-v is basically my shell launching the process. And the second exec-v is this one, exec-v bin sh. This is your syscall that launched exec-v. If you notice, this exec-v syscall has 3 parameters. The first is a pointer to the binary, and the second and third seem to contain some interesting stuff. We don't know what that is yet. So what we can do is we can refer to the syscall table. Every operating system publishes a list of syscalls. You can find it in the C development headers. Or actually, yesterday I found somebody had made this really lovely website which gives you a list of all the syscalls with different platforms. So I'm going to show you that. The website is called ARM64.syscall.sh. I'm placing this on the live notes. I'm going to drop this on Discord as well. Let me show you. the syscall table. Now here's a syscall table. You can search for execve. The first column is syscall number. That is the number that should go into X8. This is the syscall name, execve. This is the value dd in hexadecimal, which should be populated in X8. This is parameter 1, pointer to file name. Second parameter, pointer to argv array. Third parameter, pointer to environment variables. Now, how do you supply parameters to syscalls? Well, you supply them by registers. So you set X8 to the syscall number, set X0 to the first argument, set X1 to the second argument, set X to the third argument, 4, 5, 6, and up to 7 arguments you can pass using syscalls. So now let us see this in action. Let us see how to invoke a syscall for execve. We're going to simplify this a little bit. For execve, we are not going to supply argv. We're not going to supply the environment variables. We'll simply leave them as null pointers. Let us study exec1.s. Now you see over here how we've organized exec1.s. We have to set 3 parameters. X0 should be a pointer to a string. And we saw earlier how to use PC relative addresses. It's with this instruction ADR. So you simply say ADR X0 and the label shell. The shell contains the string bin sh with a null terminator. The next two are argv. We're going to leave this as null, no arguments passed. NP, no environment variables passed, that's null as well. And this is syscall number for execve, that is an X8. And svc0 is the interrupt to kernel. It's called supervisor call. So here's your code, that is exec1.s. Now let me compile this code. I can do build ASM, but I also have another utility called build shellcode, which is quite nice because it gives me a disassembly view and null bytes and whatnot. So it assembles it, it links it, and here you can see the disassembly, ADR, move, SVC. And here is the literal pool with the string bin sh, null terminated. The length of the shell code is 28 bytes. It does contain null bytes, but it works. First, let's see this in action. I'm going to paste this on the live notes as well, just for your reference. And now you're going to run exec1.elf. It drops you into a shell. You exit, this thing works. Now, a side note over here. When we did ARM32 shell coding, one of the tricks we employed to make the shellcode compact as well as make it free of null bytes was the use of thumb instructions. And in ARM32, thumb instructions are just 16 bits long, as opposed to 32 bits long in ARM mode. In ARM64, there's no concept of thumb instructions. All instructions will be 32 bits long, no matter what. So getting rid of null bytes is going to be fairly complex. There's another caveat to this, though. In some exploits in ARM64, you will need to supply null bytes in addresses because your user space is always prefixed with 2 null bytes. So at least 1 null byte has to be supplied no matter what. Your classic string copy like exploits become very, very hard unless you find some really interesting instruction to pivot to, but otherwise it's difficult to pull off purely null byte free exploits in the ARM64 arena. So for all practical purposes, this shellcode will do the job. I will still show you how to get rid of null bytes in the shellcode a little bit. Yeah, first let's try and minimize the null bytes, then we'll see how to. I'll give you a demo with a vulnerable program, and then we'll see how that goes. If I look at exec2.s, this shellcode has most of the null bytes eliminated. So if I compare, the first instruction is the same. Now the first instruction ADR has a lot of null bytes in here. It has like 0, 0, 0, 0, 2 null bytes are in here. So this is going to be hard to get rid of. The second instruction, move x1, 0, move x2, 0, there's null bytes over here. This is a null byte. This is a null byte. These can, however, be easily removed if instead of a 0, we just use the register xzr instead. So you do move x1, xzr, move x2, xzr. These will be no longer represented as zeros, but this will result into no null byte instructions. Move x8, 221, no null bytes there. Now SVC0 has null bytes, but here you can, the kernels ignore this number 0, so you can just place FFFF. That gets rid of these null bytes. At the end, you have bin sh0. Let me build shellcode exec2.s. And now you notice that most of the null bytes, and here there were a lot of null bytes. Here there's null bytes in the first instruction and the null byte at the end of this null terminator string. Otherwise, all the null bytes have gone. This also works. So notice how xzr has changed these instructions. There are no null bytes in there. SVC has also changed. No null bytes in there. First, let's see if this thing runs. No, it doesn't give us a signal. This runs, and it works out quite well. You still get a shell. Now, the question is it going to be possible to create entirely null byte free shellcode? I'm going to give you the solution. I'm going to let you figure out how this has happened, because you need to study a little bit of ARM assembly syntax and work with this. But here is ARM64 exec-v shellcode entirely free of null bytes. I'm going to give you a very brief walkthrough of it. I've changed it up a little bit. You set zero into x1 and x2. You set the syscall in x8. But I have a label over here called getPC. This is like an old x86 shellcoding trick. If you want to get the value of the program counter in the register, right? You like do a call to the end of your shellcode and then a jump back and then copy it from the stack pointer. Here I'm doing something quite interesting. I'm going to set x15 as this address, getPC. Now what it's going to do is this is going to generate a PC relative offset. But typically you had PC relative offsets ahead of your instruction. This label is behind your instruction. And the offset, therefore, is going to be a negative offset, which will not contain any null bytes. But then I have to do something weird, because if I want to overwrite this X, these next instructions are getting ready to write a 0 at this X location. And that's why I've added these add, subtract, and store B. You can see these label arithmetic being used in the assembler. I will let you work out what these things do as a take-home exercise. But let me assemble this. The shellcode size is increased a little bit. It's become 40 bytes. But you can see that the shellcode contains no null bytes whatsoever, entirely null byte free. And if you run, it runs. Now, does this really work in an exploit? That's the proof that I'm going to show you. The discussion of the full exploit is out of scope. We don't have either the scope or the time in this workshop, but I'm going to show you a simple Stack Overflow and how we can use this shellcode in that Stack Overflow and make the exploit work. This is going to be largely demo. The vulnerable program is called victim64.c. So it asks you your name, then invokes function 1. Function 1 has a character array of 80 bytes, and it requests the name from input getSname. And then it prints welcome %s, welcome to this person. And then it comes back to end. Obviously, the buffer overflow is in this getS instruction, because what will happen if you keep typing beyond 80 bytes? It's going to go overflow the stack frame. It's going to go overflow this local variable and eventually the stack frame. I'm going to make this. Now, while I make this, I want to point out that first, ASLR is turned off. We're not dealing with exploit mitigations in this demo. And second is I have deliberately turned the stack to executable because we're not dealing with ROP chains either in this example. I'm going to run victim1, victim4064.elf. What's your name? My name is Saumil Shah. It says welcome, and it's great. I was very polite. The next time I'm going to run it, I'm not going to be so polite. I now have a very, very long name. It sounds like a screen. Now, when I run this, I get a segmentation fault core dumped. Let's see what this looks like inside GDB. This is a classic Stack Overflow. Let me run this. Now I'm going to generate, ask your name, blah, 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 blah. Here we go. It received a segmentation fault. And notice my program counter is 41414141. But the leading bytes are zeros. This is like 0041414141. 00 and then 7 times 41414141. My stack memory is A, all this stuff. Now, if I really want to do a nice exploit, what I can do is I can align my shellcode at the stack, and I set my program counter to the stack address 00FFFFFFEE20, return to stack. If I check the memory, the stack is executable. So this thing should work. I'm going to show you the final exploit in place. Now here I have the exploit script. I'm going to plug in some values really quickly. So right now my shellcode is a bunch of NOP instructions and a breakpoint. I've calculated the offsets. I've calculated that it's taking 88 A's until you control the program counter. And here my program counter is set to 42, 42, 42, 42. Instead, what I'm going to do is I'm going to make my program counter to be this hard-coded address on the stack. And then my shellcode is going to be 8 times NOP and breakpoints. Now let me see if this leads me to the breakpoint. This exploit script leads me to the breakpoint. If I run this exploit script, it's dumping out the string, which is supposed to be my name. And this string, I'm going to pipe it to victim64. So when it asks me for the input, this exploit script is going to shove in this string in the standard input to victim64. And we should see a core dump. Now here is something really interesting. It says, may I ask you the name? And then the name went in. It wrote welcome and illegal instruction core dumped. I have a core file sitting here. I can also run this inside GDB. I can do something like exploit3.py, output it to temp name. And I can do GDB victim 64.elf. I'm going to run it with temp name redirected in. Now notice the error. It said that the program received sig trap, trace breakpoint trap. That means a breakpoint instruction was hit. If you look at where the stack pointer is, it is at FFEE20. Oops. If you look at the stack pointer is at FFEE20. Program counter FFEE40. And here we can see the stack pointer is pointing to all this D5030201. All these D5 instructions, these are NOP instructions. And this last instruction over here is a break instruction. If I show you like 10 instructions disassembled from the stack pointer, you see it's like NOP, 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 and breakpoint. This is undefined instruction. So what happened is a program counter landed here at FFEE20. It went through all this NOP, 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 hit the breakpoint, and then it stopped. What if we replace this shellcode with the exact shellcode that we just generated? And that's what I'm going to do for the final demo. I'm going to take the shellcode, the null byte-free shellcode that we generated. I'm going to comment this out. I'm going to do this NOP times 8 plus the string. This is the generated shellcode. Now, with any luck, it should not core dump us, but should give us a shell. Of course, for shell, I need like IO. So once I send in my name, I should keep the standard inputs open. And let me see if exploit 3 generates the string. Yep, it's generating the string all right. I can do this, exploit 3, semicolon cat, pipe it to victim64.l. May I ask your name? And now it's waiting. If I, oh, did an illegal instruction. Sorry. I do that. Let's see. Yeah, I had a problem in the offset. I know I had to fix it. But yeah, now when I fix the offset, because sometimes the stack moves a little bit, that's why I wanted to fall in the middle of the NOP sled. That's a short explanation. Yeah, now I have a shell waiting for me and everything works well. The shell code is working and the program is exploited. So this was like a very, very accelerated fly past of the world of ARM64 exploitation. I'm going to go back to the slides for a little bit. Right. So we've seen, like I said, the tip of the iceberg. There's a lot more to be explored. We've hardly touched upon the differences between ARM32 and 64. There's a lot more nuances about ARM64 instructions, 64-bit virtual addressing and space, like what are the address ranges and how do you work with these 48 bits. There's a lot more about that as well. We also explored simple shellcode. There's more we can do with the shellcode. Number of other instructions that we simply didn't look at. There are instructions which will do arithmetic operations between 32 bits and 42-bit values, signed extensions, unsigned extensions. There are branch instructions which we didn't cover at all. The use of the link register, prologues and epilogues. There's also a lot more exploits that we need to write in this area. And lastly, exploit mitigation technology still exists. And ARM64 ROP chains are, in a nutshell, insane. Intel ROP chains are pretty hideous, but you can still understand them. You can make them work. Then when I started teaching ARM32, I did ARM32 ROP chains. Beautiful. They're like pearls, gems, elegant, cute. Fell in love with them. Now going back to ARM64, it's like the worst of both worlds. These ROP chains are hairy and horrid. So, but they are extremely, it's also hard to find gadgets in the ARM64 space. But once you do put a ROP chain together, it is extremely gratifying. Like, I'll show you what a ARM64 ROP chain looks like. And you can appreciate how this goes. I mean, these are the ROP chains over here. You've got some crazy stuff that you need to do in order to get your ROP chains, bypass data execution prevention and whatnot. So this is all the stuff that I'm putting together for my class. This is going to be the first time that I'm going to teach the ARM64 Exploit Laboratory in the public domain. The class is open for registration on the Ringzer0 website, and it is going to be delivered virtually February 19th to the 24th of 2023. And in this class, we're going to cover basically all the stuff that I just talked about. We're going to see what it takes to exploit binaries in the 64-bit space. We're going to see how to bypass exploit mitigations. We're going to learn about ARM return-oriented programming. I mean, this is not going to enable you to write the next iOS 0 day. It's far from that. But it gets you a very good base for exploitation on Linux on ARM64 or any Unix-like derivative on ARM64, the core concepts. And then, of course, with Android and iOS, you can build up based on these core concepts, what nuances these other operating systems have to offer. A little bit about resources. Where do you go from here? Unfortunately, I have not really found many good resources yet. Like, there are a few books. The books are purely academic. They're more like a simplified version of the ARM64 instruction set. Gives you an overview of the instructions and assembly, but there's no really good books that put everything together. I've also not found any interesting blog posts or references about generic ARM64 exploitation. The CTF challenges and some of the tutorials about ARM64, they're more like, okay, here is a hidden jackpot function inside this binary. Can you use control the program counter and invoke this jackpot function? Or can you return to this unlock function? I mean, that's all great, but these jackpot and unlock functions don't exist in real world binaries. What are you going to do? How do you exploit like general purpose web servers and all? So that's all. I haven't found any good material on that. I guess people are still busy with 32-bit exploitation space or diving into iOS kernel and other stuff. But I'm sure as the world moves towards ARM64 coming on general desktops, there's going to be some material published in here as well. With regards to 32, if you wish, you can look at a few tutorials in ARM32. That's a good starting point. Get familiar with ARM32, then move on to ARM64. If you go to the Ringzer0 Vimeo site, let me see if I can pull that up. There's a number of free workshops. Some of the workshops are on writing ARM shellcode, which I've taught, debugging with Emacs, and a few interesting things which you could try from. And this page archives all the free workshop videos that we've published over the past 3 years. And there's some interesting material out there, and you can pick it up and try as well. Few closing comments. Now, if you're interested in more stuff, first let me show you what's coming up next in Return to Exploit. The third and final workshop in Return to Workshops is going to be taught by Jean-Philippe Omasson. JP is a modest wizard of cryptography. He's probably one of the sharpest people out there that I know. He's authored a few crypto ciphers. He knows bloody well what he's doing. He's authored 2 books on cryptography. And JP is going to teach an introduction to cryptography, which will be very interesting. I mean, I'm going to attend it, even though I know a bit of cryptography, but this is all about applied cryptography. And if you're interested in his workshop, the registrations are still open. His workshop's going to be taught on the 21st of December at 8 a.m. Pacific time. It's free. And please join that workshop and tell your friends. For those of you who have attended today's workshop, you'll get a little gift in your inboxes tomorrow. Look at it. I also want to remind you that early bird registration for Return to Exploit is still on. And early bird registration will close in 15 days, come the 31st of December. In January, we're going to go to regular pricing. So the time is now. If you have any folks you're interested, any folks you know who are interested or yourselves, make good use of the discount, and definitely look for that little present that's going to come your way tomorrow. For announcements on when we're going to publish the videos, follow us on Twitter and Mastodon. If you wish to email us, here are our email addresses. And by the way, grab a copy of these live notes. On the top toolbar, you'll be able to see some download buttons. Just click on download and grab the text file, keep it with you. It's interesting. And in addition to the virtual event Return to Exploit, we are also going to return back to Las Vegas in person with our August event titled Ringzer0 Gravity. So that's pretty much it from me for this evening. The floor is open to any questions that you may have. I'll be happy to answer them, or at least make up a meaningful answer. So fire away your questions on Discord or on Zoom Q&A. I want to especially thank Guven for hanging around today. For those of you who are wondering what's this cat doing on the Zoom screen, that's Tiger. That's Guven's lucky mascot. Guven Bairam, a brief introduction, is a very dear friend of mine. He's now also a Ringzer0 instructor. He's going to be teaching a class at Return to Exploit on hardware level attacks to get you software access. It's a class about do-it-yourself implants and glitching and all sorts of fun stuff that you can play with hands-on hardware. I'm really looking forward to that training as well. All right, questions coming up. Coven's Tiger's butler. Aren't you lucky? Aren't you Lucky's butler too? Lucky is his other cat, by the way. Right. Well, folks, thank you very much for taking time out today. Thank you for joining the workshop. I also recognize a few of you from places we've met before. So good to see you. Good to see you around. It's been a blast. I enjoyed teaching this, and I look forward to meeting you folks sometime, somewhere. So stay safe and have a good evening or a good night or a good remainder of the day wherever you are. I'm going to end this workshop, and thank you very much for your time and attention.